Good morning, guys.
Good morning, ma'am.
Good morning. I hope everybody is able to hear my voice properly.
Yep.
Yeah, I request everybody to please use chat box instead of unmuting and speaking. That will be great. Thank you, guys. Right. Good morning, and thank you so much for your response in chat box. Right. So, welcome to HIW, guys. How are you all? Right. Thank you. Thank you. Thank you for your response. I am Bhavya from HIW team. As part of our 100 webinars mission, we have today conducting our 31st webinar on harmonic analysis using ETAP tools. So we HIW are the finishing school who will bridge the gap between the industry and the academic, right? We give the training on industry-oriented training and also help them to get into the right career. Today, I would introduce Mr. Santosh, sir. Hi, Santosh, sir.
Yeah, hi, Bhavya.
Right. I'll just take 2 minutes of time to just introduce Santosh, sir. Santosh, sir has 10 years of experience in electrical power system analysis and also the conceptual electrical design and technical consulting guys. For electrical power, generating plants, transmission and distribution systems, oil and gas fields, and also various industrial segments. He is also into the very much conservant with the Ieee standards. He has worked for the SEC, Karama, Qatar, and also has good experience on the industrial design engineering tools like PSCAD, ETAP, CIME, PSSE, CDEGS, and manpower, right? It over to you, sir. Santosh sir.
Yeah, thank you, Bhavya, for introducing me. Good morning, everyone. Welcome to the session Harmonic Analysis using ETAP. So I would like to thank HIEE for giving me this opportunity, and I appreciate the efforts of Mr. Madan and his team in empowering the electrical engineers. And also, I wish them all success in 100 webinars in this year. So let us start this session. Okay. So in this session, we are going to see what are harmonics, what causes harmonics, what are the effects of harmonics, and how to model harmonics and perform a study in ETAP. And also we are going to see what is the importance of performing a harmonic analysis by taking a small or simple example models. And also we are going to see a hand calculation to verify those results. Okay. So, okay, let us start with what are harmonics. Okay. The presence of harmonics in electrical system means that the current and voltage are distorted and deviate from the sinusoidal waveform. If you see this, when you study in your engineering, like you will be voltages and currents will be basically of a sinusoidal in nature. Okay, but due to some reasons in the system, the voltage and current waveforms will not always be the sinusoidal, and it will be a distorted waveform like this. Okay, so if you want to define what is harmonics, it's like a sinusoidal component of a periodic wave having a frequency that is an integral multiple of fundamental frequencies. So let us see what does this mean in our next slides. So in this, we are going to see what are the effects of harmonics in the power system as well. So, okay, if you see, this is a pure sinusoidal waveform of a fundamental frequency. Okay, and this particular sinusoidal waveform is of third harmonic, and this particular one is the fifth harmonic. Means it has the frequency which is of order of harmonic order into the hertz of the system. So suppose if I have a system with a 50 hertz, so my fundamental frequency will be like this, like 50 hertz, and the third harmonic will have 3 into multiples of 50, like which is 150 hertz, and fifth order will be 5 into 50, which is of 250 hertz, and the seventh harmonic will be of 350 hertz. Okay, so so if you see this particular waveform, like this is a distorted waveform, which is the summation of our fundamental and the individual harmonics frequencies. Okay, if you see the waveforms expressed as I is current actually, I is equal to Im into sine omega t. This is the fundamental waveform, and the third harmonic will have Im into sine 3 omega t minus delta. Okay, it's a phase shift. So it will be like this, like the I total, the expression for this particular distorted waveform is expressed in Im sine omega t, Im 3 sine 3 omega t, Im 5 sine omega t, like that. It's a summation of individual periodic waveforms. So we can define like a distorted waveform is the summation of a periodic sine waves of different frequencies. Like if you sum up all the fundamental third, fifth, seventh, like if you whatever available in the system, it's a summation of the individual harmonic frequencies. Okay, and at the same time you can resolve this particular distorted waveform into a fundamental, and also the summation of fundamental and the the other harmonics will give the distorted waveform. Like this is what we have studied in our engineering, which is in the Fourier analysis. Okay. Okay. So what are the causes for this distorted waveforms in the system? So before that, we need to see what are the types of loads we have in our electrical system. Like there are two types of loads. One is the linear and the another is the non-linear loads. What are the linear loads? Linear loads are like the loads which follows the Ohm's law, like the relation between the voltage and current waveforms are sinusoidal. So that I'm going to show it in our next slide. And for the non-linear loads, the current is not proportional to the voltage. It means that the current it draws does not have the same waveform as the supply voltage. So let me show what this means. Okay. So if you see here, the linear loads, if you see any resistive load or inductive load or a capacitive load, this is your sine wave. Okay. And this particular this particular is the voltage wave, and this particular one will be the current wave. Okay. Like it's like a multiplication, like based on your resistance value. Okay. The voltage will be equal to R times of your current. Okay. So the voltage and the current will be in the same phase, and both will be in the sinusoidal form. Okay. Whereas if you have an inductive, here also you will be having both current and voltage will be a sinusoidal waveform, but there will be a phase shift. It lacks the voltage, like current lacks the voltage. At the same time, the capacitive also you will be having a similar sinusoidal waveform, like you will be having both voltage and current in the sinusoidal waveform with a phase shift of 90 degrees, which is in the leading. Okay. Whereas in the nonlinear loads, if you see here, you will be having a source and you will be having a resistor, and by using the firing angles, like you will be having a positive and a negative side of switches. Like for positive side, you are going to fire at particular point where you will capture the okay. Yeah, you are going to capture only one particular some particular point of the wave. So where you at this point only you will be having the current, and also at the negative side at this point only you will be having the current, whereas the remaining points you will be having a zero current. Okay. So it means that the voltage and current will not be a pure sinusoidal. The voltage will be pure sinusoidal. Maybe the current will not be a pure sinusoidal waveform. And these currents will also create a distortions in the system. Okay. So let us see what is the harmonic order and what is the phase sequence. So what we have seen here is a distorted waveform can be like divided into like multiple fundamental and also individual harmonics, like third, fifth, seventh, and it's like it can resolve into like multiple harmonics. So here we are going to see in our slides like what is the phase sequence of each harmonic. Okay. Okay. Each harmonic order has a particular phase sequence relationship with respect to the fundamental. By convention, the fundamental is assumed to have a positive sequence, and the higher orders we will be taking as a positive, negative, and zero sequence. What does this mean? Actually, let us see that in our next slide. Okay. Say suppose if we are assuming the fundamental like this, the RBY, this is the phase sequence, and this one is a 120 degree, and YB will take as 0, and this is minus 120 degree. Then our second harmonic will have a like we have to multiply this 2 with this this phase sequence. So what will happen? It will be 240, 0, and minus 240. So this 240 can be represented as minus 120, and minus 240 can be represented as plus 120. If you see this is 120, 0, and minus 120, and the second harmonics will have a phase sequence which is exactly opposite to the fundamental. It means that this behaves as a negative sequence component. Coming to the third harmonic, if you multiply 3 with this phase sequence, phase angles, then you will get a 360, 0, and 360. 360 can be represented as the 0 degree, and minus 360 can also be represented as the 0 degree. It means that it has a magnitude, it has no direction. So these are can be represented as a 0 sequence components. So if you see the harmonics, like if you see the harmonic 1, 2, 3, 4, 5, 6, 7, 8, 9. So we can see first harmonic, if you are assuming as a positive sequence, the second will be a negative sequence, third will be a 0 sequence. Similarly, the fourth will be the positive sequence again, fifth will be negative, and sixth will be the 0. So like that, it follows. So if you see this, the positive sequence, negative sequence, and the 0 sequence, the fundamental 4th, 7th, 10th, and these numbers will come under the positive sequence. This can be like if you can also get a formula like 3n minus 2. Similarly, for the negative sequence, we can take as a 3n plus 2, and for the 0 sequence, it's a 3n. So this we can guess like what is the phase sequence of each harmonic order. Coming to the types of harmonics in the power system, we have two types. Like one is the characteristic harmonics, and another is the non-characteristic harmonics. The characteristic harmonics are generated, the harmonics which are generated by a P-pulse power converters. It can be given by a formula H equal to Pn plus or minus 1, where P is the number of pulses. If you have a 6 pulse, this P will be 6 pulse, and if you have a 12 pulse, it will be 12. Okay. And whereas n can be 1, 2, 3, 4 like that. So you have some fixed kind of characteristics, like it can be defined like this. Okay. In the non-characteristic harmonics, like you have a interharmonics. Let's say suppose basically in the characteristic harmonics, the harmonics will be of the integers. Like you can have 1, 2, 3, 4, 5, 6. Like it's a kind of number. Whereas in the non-characteristic harmonics, like in the interharmonics, you can also have a interharmonics. Like you can have a 5.1 or 5.2 some kind of real number kind of harmonics. Basically, these are generated by the AC converters, so cycloconverters, which converts AC to AC. And there are like subharmonics, which are having a frequency less than the system frequency. If you have a 50 hertz system, you will be having a harmonics whose frequency is less than 50 hertz. Basically, these harmonics harmonics can be seen in the system. These are the responsible for the light flickering. Okay, and there are the triplen harmonics. We can see that it's odd multiples of like odd multiples of the third harmonics. If you see here, the harmonics which are covering under this 0 sequence, like third, sixth, ninth, and this all covers under the triplen harmonics. So these do not have any direction, but it has a magnitude. These currents basically blocked in the system because of if there is any ungrounded networks. Okay, let us see the next slide. Okay, what are the effects of harmonics? If you see if you want to see what's the effects of the harmonics in the harmonic power system, there is a immediate effects which causes like what we call resonances in the system, poor power factors, reduction of power engine, and high currents in the neutral, overloading of the conductor, and malfunctioning of regulating devices, increase in noise and vibrations. These are some immediate efforts. Because of this harmonics, it causes the immediate efforts. And also over a long time and a medium time, like it will reduce the life of the equipment, and also aging of insulation and dielectric, and it's an economic cost. If you see that, if you see individually, like conductors will have a overheating, and there will be overcurrent in the neutral conductor, and there will be a skin effect. And for the transformers, there's overheating and additional losses. And for rotating machines, it will be a braking torque and vibrating torque. For the capacitors, overheating. And for the other devices, like it stop unexpectedly, or incorrect measurements or incorrect operations. So there are multiple effects of harmonics in the electrical system. So so we have to basically how quantify what is the harmonic content in the system. Like there are some indices which will help us to see what is the harmonic content in our system. To measure that, we have some indices like the total harmonic distortion, which will total harmonic distortion, which will be a voltage, and also for the current, which will be given as a root mean square of individual harmonics by fundamental voltage. And similarly, for the total harmonic distortion for the current, it will be root mean square of individual harmonic currents by fundamental current. And also the total demand distortion, this is for the current. This is root mean square of individual harmonics by the load current. And there are other factors like telephone influence factor and C message index, and IT and VT products, K factor, displacement and distortion, total power factor. These are certain indices to measure the to see what is the harmonic contents in the electrical power. So let us see what IEEE standard says. This is the taken from the IEEE 519. For each voltage, like up till 69 kV and under, the individual harmonics are defined up till 3%, and the total harmonic distortion is defined up till 5%. Means it is allowed. Like in your system, you should not exceed more than 3% of individual harmonic voltages, and the total harmonic distortion in the system shall not exceed more than 5% for 69 kV and under. And for 69 to 161, it is 1.5%, and also it's for individual, and 2.5% for the total harmonic distortion. Similarly, for the 161 kV and above, it is around this is 1% for the individual, and around 1.5% for the total. Similarly, this is for the voltage, and for the current distortion limits, for each harmonic, and also the total distortions are defined in IEEE. So we need to basically maintain our harmonics below the standard limits were specified by IEEE 519. So so these are the measures, like what we have to maintain this much voltage and current limits. But let us see where we need to measure this. Okay, say suppose this is your system. Say suppose you are the customer understudy. So you are connected with a transformer, and the transformer primary is connected to a utility system. This particular thing is a utility system. So your limits, like harmonic content at this point, shall be below IEEE 519 limits. Say suppose if this is the system. Okay. Okay, let me explain this first. So this is your house load, and your house load has some nonlinear devices which creates harmonics, and you are creating the harmonics, and you are injecting that to the system. When you are injecting this harmonic currents into the system, the source voltage will get distorted. When this source voltage get distorted, the loads which are already connected in the same to the same utility will also get affected. So this point will be your point of common coupling. So for this system, if you are connecting on the transformer secondary, and this is your load, so this will be your point of common coupling. So here you need to maintain the harmonics within the limit. So how to mitigate the harmonics? If you have a system which has which is having more harmonics, so we need to reduce the harmonics, because we should not affect the other systems which are connected to the same utility. So there are two for academic point of view, there are, like, we can see these two, passive and active filters.
Santosh sir, sorry to interrupt. Actually, there is so much of background disturbance coming around.
From my side?
Yes, sir. Yes. Now it's fine, sir. Maybe there is some tapping sound that is coming from behind.
Okay. Maybe
Little
some.
louder, sir. Little louder. That's it.
Sure. Okay. I can speak a bit louder.
Yeah. Thank you, sir.
Okay. So we have two types of filters. One is the passive filter, another other is the active filter. The passive filter is like a series combination of capacitor and the series reactor, and it is tuned to a specified harmonic frequency that we are going to see in the our next slides. So this particular filter, what it does is, if your system is creating some harmonics like 5th, 7th, or 11th and 13th, there it is like your loads are creating these particular harmonics. So what we need to do is we need to put a filter. Filter is basically like a capacitor and a reactor in series. This has to be tuned. Like if it is tuned for 5th harmonic, whatever the harmonics generated in that system, it will pass to that one. Let me show you that in the next slide. Yeah, if you see here, basically this is your system and these are your loads, like non-linear loads. Then always the harmonics will try to flow to the lowest impedance path. So basically, whatever the harmonics generated at your load points, those will flow towards the source, since there is no other points which from to where it can go. So it will try to flow towards the source. When you place a filter, so what it will do is certain particular, like if this particular filter is designed for 5th harmonic, so this whatever the harmonics 5th harmonic generated in this nonlinear load, this will pass to this particular filter and it will flow to the ground. So the current which is flowing towards the source will not have any 5th harmonic. Example. Okay. So yeah. So this is the concept of the passive filter. Whereas in the active filter consists of a power electronic. It's a power consists of power electronics. What it does is it will generate the currents which is exactly opposite to the currents which are generated by the nonlinear loads. It's the opposite phase with the same amplitude, and it will both get cancel out each other, and the harmonics in the system will be nullified. Okay, so I will show you that. Yeah, this is the system, the schematic of the active filter. If you see, this is the load with harmonics. So this particular load is generating some harmonics. So this is the pattern. Okay, and this is the active filter. This active filter will be designed such a way that it will inject the harmonic currents, the currents which are opposite to the harmonic currents. So these both will get cancelled out each other. So the current which is coming here will be a pure sinusoidal waveform. Okay. So this is the concept of the active filter, and there are types of passive filters like a single tune, bypass, high pass, and high pass undamped, and damped, and third harmonic damped, and third order C-type filters. So how to design these filters, that we can see in our future sessions. But in this session, I'm just going to use some values to show you for a typical filter, but how to design these filters can be discussed separately. This is not part of this lecture. Okay. So yeah, coming to the system resonance. So basically our electrical networks are inductive in nature. So the complete system will be in an inductive. When you are placing any filters, or if you want to place any capacitor banks in your system, what does it happen? Your system inductance and this capacitor can form a it will be like a RLC circuit, and it may resonate at any particular frequency. Say suppose if you this is the concept of resonance. If you see the series resonance occurs in a series RLC circuit when the inductive and capacitive reactances are equal. In this case, the circuit impedance is very low. Correct, right? So what will happen? If you have L and C are equal, this both will get like cancel out, and then the impedance of the system will be very low. like it will be like in this condition. Like if you see this particular point, this is your system impedance, and at this point where your this is like your series resonance condition, where your series reactance and series capacitance will get equal, and the system impedance will be very low. In this condition, even a very small exciting voltage will leads to very high currents. Basically, if you are tuning a filter like this, okay, where your L and C values are get cancelled out each other because of the resonance condition, the harmonic current which is generated here for one particular, like say suppose 11th harmonic, at 11th harmonic, this our L and C values are getting cancel out each other. So this 11th harmonic current will directly flow to this particular go to the ground. So here in the series resonance, we have to see like there is no exciting voltage which causes a high current. This I will show you in the ETAP how it happens. And also the parallel resonance is like in a parallel RC circuit with equal inductive and capacitive reactance. So this happens in the parallel conditioning of inductive and capacitance. In this case, the circuit admittance is low. A small exciting current develops a large voltage. If you see here, in this condition, the impedance is very high, means admittance is very low in this condition. A small current here will get amplified, and it will create a very high voltages. So we will see how to see this series and parallel resonance in the system in our ETAP example. So let us go to some ETAP. Like let us do a small study. Till now, whatever we have seen this slide. So let me create a small example and show you what happened. I'm creating one new project with the name Harmonics.
Sir, sorry to interrupt. Your screen is not visible. Your ETAP screen is not visible.
Okay, fine. Sure. You see now?
Yes, sir. Yeah.
Yeah, I'm creating a new file. Okay, I think. Okay. Yeah, I'm creating a new file with the project name as Harmonics and with a 50 Hertz system. Okay, what I do is let me take a real example. So basically, this a data sheet for the nonlinear loads. Basically, this is for one power converter, wherein the ABB he has provided the data like this. He will be giving distortion limits like this for fifth harmonic. What is the voltage? What's the individual fifth harmonic voltage? 7th, 11th, and like this. Similarly, he will provide the current harmonic distortions like 5th, 7th, 11th, 13th, 17th, 19th. Like he will provide all the individual harmonic current as well. So let us model this particular converter in our ETA. So what I do is, yeah. Can you see the data sheet?
Yes, sir, we do see, but actually there is a lot of disturbance which is actually disturbing the session, sir.
Sorry, some construction work is going on, I guess. The next building. Let me see. Okay. Sorry for that. It's in the next building, I guess.
Thank you.
Yeah. So what I will do is, I will just take. Okay. This is the equivalent source, and I will place one bus. I will place one cable. I will explain why I'm taking this cable. And I will place one more bus here. And I will place one a static low. Okay. So for the source, what is the voltage he has given? The source voltage is 11 kV. And further regarding the short circuit, he said around 76 MVA. So I consider three phase and single phase same. And I consider this as a pure inductive circuit. Okay, so I consider, like, if you see, I am considering this as a pure inductive circuit for a time being. So I will be having a very high Otsora ratio. It means that it's a pure inductive. And then I just connect this grid to a bus, and then I will take this cable because, like, since it's a new model without any impedance impedance in the system, ETAP will not resolve the will not give the results for this. So I just take one cable of it's 11 kV cable. Take this as a 3-core XLPU. I'll take a maximum 400 square mm, and I'll just keep this as a 1 meter. It means it has a very minor system, and I just will connect this load to this particular system. Okay, and the load details will be in here. What he is giving is the 156.3 demand load current with a power factor of 96.6. 96.3 and with a power factor of 96.6. So this is my load. So this is my harmonic module. When I go here, as of now, I didn't inject any harmonics. I'm just running a harmonic load flow. Before that, I will show you, like, what is the study case. In the study case, we need to specify what is the initial load flow, whether you are going to use adaptive Newton-Raphson or Newton-Raphson method. So you need to define this, and this is generating and loading categories. That comes, like, you are going to see what type of what exactly you are taking in this rating page. Okay, and in the loading page, what exactly you are taking. So I just take design, which is having some value. So in the plot option, I need to select these buses to see the results on these two buses. And on the cable, I want to see the cable one. Okay, so these are the elements I have in the system. And then coming to the model, I will take a ideal current source. And I do not want to consider any harmonic content. This I will explain in the next, like, once we go in detail. But I'm just modeling a simple system. If you want to take any adjustments, you can take it here. So let me just run a harmonic load flow. This is a harmonic load flow button. So I just select, just give some output report name as HA, and then run this file. Currently, this particular load is acting as a linear load. It means that it's not injecting any harmonics. See this? This particular value is the voltage total harmonic distortion, which is 0. And this is the current total harmonic distortion, which is also 0, because my load is a pure resistive kind of load now, which obeys the Ohm's law, where if you can also see plot and bus 2, and I want to see the waveform of this one. Can you see this? It's a pure sinusoidal waveform. So now what I do is I will inject the harmonics as specified this ABB vendor. So I am just going to use this. I'm going to create a harmonic model in the ETAP, and I'm going to inject these particular harmonics. So how to do that? Yeah. Double click on the hashtag load, go to the harmonics page, and there is a harmonic library. Like you can see, there are some default libraries available in ETAP. Say suppose if I take Rockwell 6 pulse VFD, these particular VFD will inject a harmonic current in this pattern. If you take 12 pulse VFD, it will inject the harmonics in this pattern. Okay. So, but I want to inject the harmonics which I have in my data sheet. So what I will do, I will go to a library. I will create one harmonic source here. I want to give this as a different name. Okay. I want to put this is a ABB only. I want to put this as a test model. Okay. And this is the current source. Okay. And if you want to include the interharmonics, means if you want to include the harmonics which are not integers, like if you want to put a 5.1, 5.2, something like that, if you can also include that. But in our datasheet, if you see, we have only the actual integer numbers only. So I will not select this. So just click on OK. And in this text, you have to just click on edit. And I have a 50 hertz system. Okay. I have a fundamental of 156.3. And here I need to add these particular harmonics. So what all we have? 5th, 7th, 13, 11, 13. So here I will put 5, 7, 11, 13, 17, 19. 23, 25, 29, 31. So these are the harmonic orders available in the datasheet, and they have provided what is the harmonic injections by this converter into the system. This is the guaranteed values, like the vendor will specify his converter will inject this much harmonics into the system. He will do a test in this factory, and he will give us this data sheet to us. So let us put these values here. What is this? If you see, this is a pure sinusoidal waveform, because since I have not entered any other harmonic contents here. So here I will put 2.1%. Okay. And then this is 1.2. So you can see this, and also this, you observe this waveform, it will be slightly getting distorted. So this is 5.3. See, can you see this? There is a distortion in the waveform. And this is 3.5. Can you see more distortion in this? And 0.2, 0.1, 0.9, 0.9. 41 and 43 harmonics are 0 and 47 is 0.2. 49 is also 0.2. So if you see, after entering this data, the sinusoidal waveform has got distorted here like this because of the harmonic contents available in the system, like this particular, the harmonics generated by this particular nonlinear source. Okay, so let me just click on OK and then close this and go to the system, our system, and just select this load, go to the harmonics, go to the library and select the library what we have generated here. So ABB and the model is test. Just click on OK. So you can see that waveform here. And just click on OK here now. And now again you run this load flow, harmonic load flow. Yeah. Before, if you remember, this voltage is 11 kV. Here also it's 11 kV. But there is now the voltage has become 11.01 kV because of this harmonics in the system, and the total harmonic distortion at the bus 2 is 3.31%, and at bus 1 also 3.31 because of the small cable. If you have a large cable here, then this value and this value will be different. And also this is the current harmonic distortion, which is 6.94. We can also see these values in the data sheet here. So the manufacturer has already told that the total harmonic voltage distortion is 3.31% and total harmonic current distortion is 6.93. So which is matching with our system. Okay. So if you see the waveforms, again, you can click on this harmonic analysis plot. Just select the bus 2. And I want to see the waveform of this. So it will be like this. And bus 2. And at bus 1, it will be like this. Okay. The impact of this nonlinear load on the system, you can see that. Before it was a pure sinusoidal waveform. Now it got distorted because of this nonlinear behavior. And also you can see the spectrum. So this is the spectrum of bus 1 and bus 2. What is the harmonic content seen by at the voltages? This is a voltage harmonic. This is in the order. If you want to put it in order, you can see fifth harmonic voltage, individual voltage, and 7th, 11th, 13th, 17th. These are the individual voltage harmonics. And also you can see across the cable spectrum. Close this and show you. So these are the individual harmonic currents seen by the cable. Like basically on the buses you can see the total voltage harmonic distortions, and in the cable you can see the total and individual current harmonic distortions. Okay, so let us see whether these results given by the ETAP are correct or not. Let us just quickly do what I'm doing is I'm checking whether these results are correct or not correct. So what is the grid values they have given? It's 11 kV and the fall level is 76. The frequency is 50 hertz. And I want to calculate the source reactance. I want to just calculate what is the source reactance. How to calculate the source reactance? It's voltage square by MVA, which will give the short circuit reactance, like the system, the source reactance will be given by the voltage square by the MVA. Will give this source reactance, and this is the load current, and this is the power factor they have given, and this is the harmonic contents I have taken from this particular data sheet. Okay, so these are the values I have taken here. Okay, so now what I will do is, these are given in percentages, so I will just convert this into amperes. So how to convert that in amperes? So this value is a percentage of, what's the percentage harmonic into fundamental current. This will give me, okay, this is in percentage, so I will have to divide by 100. So this is the fifth harmonic current in amperes. So what I did is, these values they have given in percentage, so that I am converting in amperes. To convert this into amperes, I'm multiplying the percentage of fifth harmonic with the fundamental current. So I got 3.2823. So similarly, what I will do, I will take for seventh harmonic current, I will take 1.2% into the fundamental by 100. So this value will be for my seventh harmonic. So like that, I can do for the remaining harmonics. What I will do, I just dollar symbol here to fix. So these are the currents for the remaining harmonics. So what basically I did is I just fixed this value, and these values are variable. So I calculated the harmonic currents in amperes. Okay. Now this is the source reactance for the fundamental current. So for let's see H. What I'm doing is, what is the impedance offered by the system for the fifth harmonic? So fifth harmonic, the frequency will be 250 hertz. So what will happen? So this value is equal to the fifth harmonic into the system reactance. So the impedance offered by system for the fifth harmonic will be 5 into the system reactance, which is equal to 7.9. So similarly, what I will do, I will just drag this one by, what I will do is 7 into this value, and this B I will put a dollar to fix that. Okay. So I have calculated the reactance of the system offered to the particular harmonic currents or particular order harmonics. So this is CH. Okay. Okay. So what I will do is, now I will calculate. Okay, fine. What I insert one option, and I will calculate IH square. Because what I have to do is, here I want to calculate ITHD and VTHD, which are given by these particular formulas. Okay. If we want to calculate the current total harmonic distortion, I have to root mean square of individual harmonics by fundamental current, right? So what I'm doing is, I am squaring up the individual currents here. So what I will do is squaring up the individual currents. So this square, so square up all the things. Now I want to calculate the voltage voltage seen by each individual harmonics. So what I will do, I will take VDH individual harmonics, which is equal to this value into this value. Okay, this is the voltage seen by each individual harmonic. So I will just keep this here, and now I will do VDH square, so which is equal to this square. Why I did this one is, so I'm using this formula now. I'm just some root mean square of individual voltage harmonic square by V fundamental. So here, what I want to do is sum of. So I'm doing for the current. So I'm doing this particular thing. Okay. Sum of IH squares. So which is equal to sum of this, all these things. Okay. And this is the square root of sum of IH square. So which is equal to okay. Now what is my fundamental current? Fundamental current is 156.3. We can see that here. So now my ITHD equal to this value divided by this value. This value into 100. I want to see it in percentage. So it is 6.94 percentage. So can you see that value here? 6.94. This is the current harmonic distortion. And let me see similarly for the voltage harmonic distortion. Now I will do the same thing here also. I will do sum of VD square is equal to sum of all these squared values. Okay. And again, I will do square root of sum of VD square, which is equal to SQRT of this value. What is my, this is fundamental current. Similarly, for me, fundamental voltage, which is equal to, I need to take the per phase voltage, which is 11 kV by √3, which is 6350.85. So now what is my VTHD? Equal to this value into 100 by this value, which is 3.3 percentage. So can you tally these values now here with the software? See, this is my VTHD value and this is my ITHD value, which will match with the calculations. Okay. So here, if by using this slider, we can also see what is the fundamental current, what is the fifth harmonic. These values, I think you can also see it in the Excel. Okay, this is the voltage offered by for fifth harmonic, 7th, 11th, like that. So here also we can see using the slider, what is the voltage offered for each individual harmonic. Okay, so this is your harmonic load flow. So let me show you how the harmonic load flow is differed from the normal load flow. What I will do, I'll just create another presentation view. So in the first window, I will show the load flow results for normal load flow, and in the second window, I will show the results for using harmonics. So in the first window, this one I will show run a normal load flow. Showing in kilowatt. Okay. Okay. And in the right window, I will do a harmonic load flow. If you see the current in the left window, the current is around 156.3, and in the right window, it is 156.7. There is a small difference in the current. This is because of the harmonics. This is because of the harmonic current. This is the RMS values, and this is the fundamental values. So let me just see So this is a very simple system where we can see the impact of harmonics. We can also do one small thing here. Since the effect is very less, so what I will do here is I'll just go to the library again, go to the text here. Instead, I have a harmonic current, which is of 5.3%. I will increase this to 15% or something higher. Okay, I'll just take something higher to show the impact of this harmonic on the system. So what I'm doing is 11th harmonic 11th harmonic current I have increased to 5.3 to 20%. Okay, so again in the load flow, what I will do, I will rerun again. Yeah, can you see this? Instead, earlier it was 156 point some change, and it is now 159.6, and also the voltage and current distortions also got increased. Okay, so so this is the impact of harmonics in the system. So suppose now what is the importance of this harmonic analysis is, say suppose the power factor in the system is around 96.6%. Say suppose I want to improve the power factor to higher, maybe around 99%, or I want to maintain a unity power factor or something like that. And someone without doing any harmonic analysis, and if we just place a capacitor bank, okay. So what I will do, I will just place one capacitor bank in the system. Okay, I'll just take a capacitor bank. So both are same, it's the same database. So I'll just show you this. I'll just to connect a capacitor bank to this particular load, and I will place some value of around 0.453, some random value. Okay, I just placed the capacitor without understanding the system behavior. I just placed a small capacitor bank here. To this capacitor bank will improve the power factor at this particular point, because whatever the capacitance reactive power required for this particular load is supplied by this capacitor. So the power factor at this point will be improved, correct? So I just placed a capacitor. I just run a load flow to show you what happens here. Yeah, earlier the power factor here is 96.6, that has improved to 99.4, correct? So let me go to the this model. I will just run a load flow. Okay, can you see here, without doing any study, if I just place a capacitor bank, earlier my THD value is around 20. Okay, now the THD value has increased to 493.7, the current distortions, and the voltage distortions has raised to 243.7. Earlier it was around 8% or something like that. It was less than 10, and that has raised to 243. And even if you see the individual harmonics, fundamental current is 151.9 amperes. If you see fifth is 3.9, and if you see seventh is 2.6, and 11th harmonic is around 112.1, and 13th harmonic is 741.6. So the system is getting resonant condition. I will show you what happened here. Okay, so just I will make this capacitor out of service. I just don't want to show this, and let me run a frequency scan. Means what is the impedance offered by the system to each individual harmonic. I am going to see that here. Okay, I just run a frequency scan, and I will just go to the plots. On bus 2, I want to see the Z magnitude. Okay, I want to see the harmonic order. If you see, this is the impedance offered by the system for each individual harmonic. Say suppose the 11th harmonic will have an impedance of this much, the 16th or 21st will have this much, Like that, each individual harmonic will have a impedance of this much. Like the system will offer this much impedance for the system. Correct? So what happens now? When I place this capacitor bank on, like when I place this capacitor and when I run this frequency scan now, okay, I'm going to the plot option. Yeah, the impedance offered for the harmonics between 11th to 15th is very high. This is the impedance and this is the harmonic order. If you see that the impedance offered by the system for this particular harmonics is very high, it means that this is a parallel resonance. The system admittance has gone very low because of the parallel combination of capacitance and inductance of the system. Okay. So here, this capacitance is getting in resonate with this condition, this particular source inductance. So whatever the small currents earlier, if you see what is my 11th and 13th harmonic, it's only just a 3.5%, which is, if you see, which is of around 5.47 amperes. My 13th order harmonic is only of 5.47 amperes. That is getting resonated in this system. Means that value will get multiplied with this particular impedance, and it will create a very high voltages in the system. So this is the reasons like where you get the system thermal heatings, there is a maloperations in the system, there is a very huge damages and other things in the system. Okay. So Bhavya, we have some more time, or I just want to show what is the impact of this capacitance using this Excel.
Yeah, you can continue, sir. Then we'll take up the discussion.
Sure. Okay. So now I will use this Excel. I will just what I will do, I will just copy this data. Okay. Now I have placed a capacitor of 0.453 MVR. Correct. What is the XC? Again, same voltage square by 0.453. This is the ohmic value. So I will use this same currents. So same. I just converted this to amperes. I just don't want to spend time on that. So fine. So this is the harmonic currents generated by this particular load. So these currents will flow to the system, and also it will flow towards the capacitor. Correct. So here I will calculate now X SC XS is same, like this value into this 500. Just use the same, yeah, this one. So I just use this same XC SC. Okay. So just take this system like it's a source reactance, and now similarly I will calculate the reactance of the capacitor XC offered for each individual harmonic. So this value equal to minus of this divided by the individual harmonic. So here H will be putting a dollar. So this is the XC value. Okay. And for me, the net X net equal to absolute of. I'm just going to take the these two are coming in parallel. Let me show you that. If I'm seeing from this point, this reactance and this reactance both will be in parallel. So what I will do is absolute of this into this divided by this plus this. So this is the net reactance seen by the system. Now I want to see the current which is flowing in the system and the source. So if you see the current division rule, yeah, if you see this is my source reactance and this is my capacitor reactance. So I want to see what is the current flowing in this one. So that will be given by this impedance into the source current divided by R1 plus R2, correct? So what I'm using that formula here. Right? Source. Okay, we which okay, do I equal to what is the current seen now? This value into this XSC divided by this plus this. Okay, this is the current going towards the source. Okay, now what I will do the squares, IS square of these values to calculate the total current harmonic distortions. So this square. Now straightforward, I will do that. ITHD equal to it's a square root of sum of individual harmonic currents to 100 by what is my fundamental current? 156.3. Can you see here? So 477. Let me just do one. Since I changed this value in the library, I'll just go and put back that value here. ABP test edit. Here I made it 20, so this is actually 5.3. I can also put that 20 in the Excel and I can make that match that calculation, but I just want to put this value back to 5.3, and I'm just running a normal harmonic load flow. If you see this value 488.6, it's so 477, maybe somewhere I missed it. Okay, no problem. It's like IDSD value is very high. Then similarly, I want to calculate the voltage individual harmonics. So what I will do here is I will use this formula. My voltage seen at this particular point will be equal to I into R1 R2 by R1 plus R2. This is your system reactance and this is your capacitor reactance. So those are in parallel actually. So I'm using that particular formula to find out the voltages. So these values are equal to what is the current seen here? this into opposite side, this value. So P net actually is correct, right? What we are doing here. I into R1 R2 by R1 plus R2. So in our case, this R net is already we have calculated R1 R2 by R1 plus R2. So this is my individual, and I will do the VI square, individual harmonic squares. Okay. Now I will do the VTHD calculations straightforward, like which is equal to square root of sum of these individual values. Okay. Divided by 11 kV by square root of 3. I am taking this phase voltages. Can you see this value? 243.39. So it is close to this. So what is happening is the system is offering very high impedance for some particular harmonic currents, which will get amplified in the system, and then the voltages will get magnified. It will give rise to very high voltages in the system. So this is the impact of the resonance in the system. So someone has to do a proper harmonic analysis. So when we are doing a harmonic analysis, we need to see that proper data of the system, like everything matters, like source impedances, cables, transformer impedances, and what is the harmonic content provided by the vendor. So these all are taken and to the account, and we have to do a simulation, and then we need to decide what is the capacitor bank requirement, and how to tune it to in order to avoid the magnification of this current and voltage harmonics in the system. Okay, so how to design a filter? Like now, as of now, I put a capacitor here, so this leads to a very high harmonic currents. And how to design a filter, that we can see it in our next sections. So we are up to here. So the disadvantage in the passive filters is the filtering characteristics are depending on the source impedances, and it can aggravate the impedances below the lowest tuned frequency. Correct. So this is the case study what we have taken now. I think yeah, I've shown this frequency scan as well. So if you have any questions.
Right, sir. So let us, guys, whoever has the questions can put. Maybe before that, we have some 2 questions.
Yeah.
So is there any possibility, possible equipment to get power factor value as 1? Question from Joseph.
Okay. Yeah, by like actually, if you are using any passive filters, we need to we have to do the study, like where we can see what is the existing power factor and how much is the reactive power requirement in the system to make the power factor close to unity, or whatever the industry standard practice. We can make the like that. But if you are using any SVCs or something like that, there is a possibility that harmonics can be mitigated and also the power factor can be maintained unity.
Right. There's a question from Nirmal Singh. Ma'am, is the power factor correction via synchronous motor is an example of active filter?
No, synchronous motor is not the, it's only a power factor improvement. It can be a support. It will help us to support the reactive power, but it's not a filter. Yeah.
Right. We have maybe Rajesh wants to ask a question. Yes, Rajesh.
Hello, sir.
Yeah, hi Rajesh.
Yeah, is my voice audible, sir?
Yeah, I can hear you.
Yeah. So actually, normally 85 to 90% of the load we are using as inductive load, sir.
Yes, yes,
So,
correct.
so that means that the power factor is going on lagging. So if I
Yes,
want to
correct.
improve the power factor, we can connect the capacitor load at the load side. Okay, capacitor bank at the load side to improve the
Exactly.
power factor.
Yes.
But practically, it is possible to make the always the power factor to be 1, sir.
Yeah, we can make the power factor to 1. Like one is dynamically and another is the fixed. If you want to make a fixed kind of thing, like you are going to put a capacitor bank, or you are going to most of the cases you will put a fixed capacitor bank, or
Yeah, of course.
the capacitor bank will have a fixed number of taps or steps, which
Mm.
will which we can adjust to maintain some power factor close to unity. Okay, but there are some other devices like SVC StatComs and all, which will help us to maintain unity power factors.
So you are focusing on the fast devices.
Yeah, exactly. Yeah,
Yeah.
we are using a
But
fast device, but it's expensive.
actually, we are saying that for the resistive load, we are maintaining the power factor to be 1. For
Resistive load.
resistive,
Okay,
yeah,
okay.
for resistive load, the power factor is always to be 1, na, sir.
Yeah, it will be close to 1. Yes.
It will be equal to 1. So that may be
Yes.
considered as a static load.
Static load. Okay. Yeah, yeah, correct. Yes.
Yeah, it's correct, na, sir?
Correct, correct. Yes.
Yeah. So
But
I have
like,
one more.
yeah, go ahead.
Sorry, sir. I have one more question, sir.
Yeah.
Actually, I'm working on ETAP, sir. I'm working on ETAP with a different analysis.
Yeah.
So I need to know how to justify the result, whether it is correct or wrong.
Yeah. So that's what I have just shown it for a small system where
Of course, sir.
yeah, I can share this Excel to the team. It's for a small system, but for the bigger system, you need to, reduce the network. Like you have to focus only of the area of one particular area, and you have to reduce the sources to the nearest points, and then
So,
you can do.
okay,
Yeah.
sir. So when I'm doing with the ETAP and also with the help of MATLAB,
Yeah.
but both are going to be, the result is slightly deviating, sir. Is there any specific reason is there, sir?
Possibilities are there. Like you need to see your system grounding. Basically, if your system is grounded, the triplet harmonics will get it will flow through the neutral and it will go to 0. Okay, if you make any ungrounded system, the third harmonic, the triplet harmonics will get blocked in the system. The harmonic content will be very high.
That means higher order harmonics you are neglecting.
Yeah, that is a different story. But what I'm saying is the flow. You have to see the flow of harmonics. Whatever the harmonics you are generating, where those are getting where they are getting grounded. Actually, that's what you need to see.
Yeah. Okay. So how to is there any the proper test input data is available for the ETAP, sir? Because there are many systems available.
Okay.
So whenever we are giving the input data for each and every the simple system or maybe a complicated system, we need to give n number of the input data. Is correct, sir? Yeah.
Yeah, but you need to know like
available, sir.
Yeah, you need to know like what all parameters are impacting your system. Like you need to know, certain times like which like there will be some parameters which will not affect your system basically.
Yeah, of course, because we are using two standards, IEC standard and ANSI standard. So most of the time we are using IEC standard and ANSI depending upon our design. But my problem, what I'm getting when I'm working with ETAP is running output. A simulation is running, sir. But I don't know how to justify the result. How to compare whether this result is correct or wrong. That's the only one thing, sir. I'm confusing.
The only thing is like
yes, sir. Yes, sir.
Yeah, you need to make sure that model first of all is the system impedances are proper. Okay, and whether the system groundings everything are you are considered correctly, and the injected harmonics, and also I showed you in the ETAP like whether your system you are considering ideal source or ideal current source, or you are taking as a Thevenin equivalent or not an equivalent.
Of course. So is there any the test book is available for ETAP, sir?
For ETAP,
especially for the input data, how to give the input data for any basic system.
Just to show you one, like I can share my screen.
Yes, sir. Yes,
sir.
Yeah, just click on this help and help search.
You're not sharing your screen, sir.
Still no? Okay, just a second. Yeah. Can you see my screen now?
Yes, sir.
Yeah. Sorry, I can just close it. Okay, so stop. Okay, fine. Just a second. Just a second. I will share, change my screen time. Desktop. Can you see now? Can you see my screen now?
Yes, we're able to see your
Yeah.
tap screen.
Yeah. If you click on this help and go to help search. Okay. And can you see the help search now?
Of course, sir.
Yeah. Here, if you see the chapter number 27, you can see what is the calculation methodologies they have used here. So these are the standards what they have used for this software. And also if you go down here, the required data, you can see what data you need to enter for each element. Like for the bus data, you need to enter this. For the 2 and 3 winding, what you need to enter. For the cables, for the transmission lines, for the DC cable, inverter. So it will clearly give you what parameters are important for each and every element. Rajesh, is it clear?
Yes, I guess, sir.
Sir, yeah, I understand, sir. So
Yeah.
whether it is applicable for the licensed version or for any trial
Yeah,
version?
it is applicable for all versions.
All version, because I have downloaded the trial version only, sir.
Okay.
With that only I'm working, and it will be applicable for 30 days, I hope. 30 to 60 days, sir, maximum.
Exactly. So when you install this software, so you will be having it in your C drive, like you can find as HTML file.
Correct.
So can you, if possible, can you send me the link, sir, to download this material?
Sure, no problem. I can give you this.
Okay. Rajesh, please
Sure.
give your free email ID in the feedback. Maybe we'll get back to you with that.
Yeah,
Okay,
definitely,
Rajesh?
sir.
Thank you.
Okay, sir, definitely. Thank you very much, sir. Happy,
No
sir. I
problem.
have updated many information, sir. I have
Okay.
many doubt I'm having, and that also I have clarified. So
Okay.
I'm very much thankful to the resource person for the valuable the information, and also the most important thing is going to be harmonic analysis using ETAP. So excellent webinar, sir. Actually, I'm happy. I'm also enjoying. Thank you very much.
Thank you very much.
Thank you, sir. Thanks a lot.
Thank you, Rajesh. We have Venkat Sriram to speak up. Sriram, you can speak.
Hi, sir.
Yeah, hi Venkat. How are you?
Yeah, I'm good, sir. Thank you so much. It was a very valuable session, sir. Sir, I have two questions.
Yeah.
One is like now we have done the harmonic analysis.
Okay.
So, what is the correct capacitor bank to be placed to improve the power factor to 99? And second question is, this is why we place a detuned reactor in series with the capacitor bank.
Exactly. Yeah. The first question is like
What should be the value of capacitor bank?
Yeah, what will be the value of capacitor? So if you want to maintain 0.99, like you have a formulas like megawatt into tan delta minus tan.
Yes. That formula I know, sir. But with respect to harmonic analysis, I was asking.
Exactly. Yeah. That's what. So first thing is, what is a capacitor bank required for your system? That you will do it as a normal load flow, where we can also do it as a this will cover as a power factor correction for your system, where you will see by varying your load, what is the capacitor bank requirement, how many stages are required, that you will see it in your normal load flow. Once you decide what is the capacitor bank required, then as I said, when you are connecting to your system, you need to do a basic harmonic analysis to see whether the system is getting a resonance condition, like either series or parallel resonance. And accordingly, you need to fine tune, like how to design a filter, that we will come up with the other sessions. Like I have other few sessions with Ieee, where I can give you how to design a filter, active, basically a passive filters in the ETAP. Okay.
Right. Oh, there's a question from Joseph, sir. Just a moment. Is it possible to use supercapacitors to get harmonic less PF?
Super capacitors.
Yeah.
Yeah, but actually, you have to make sure whether this is making like you need to do a prior harmonic analysis. That's what I suggest to see the impact of this resonance on.
There's a question from somebody in harmonics: how to increase the phase value?
Phase values of harmonic means I didn't understand the question.
No, the question is half. Maybe the name is also not available, sir. Okay. I hope he has put it in this. Then what software he used, sir? Okay.
We have,
ETAP.
yeah, we can use ETAP. It's a very simple, and also there is other softwares like Sime and Scheme. There are many other tools, and even my power also can do harmonics.
Yes, yes. So guys, I think we are done with the questions. Guys, if you have any questions, you can raise your hand. I'll unmute you, or you can post your question in the chat box. I'll just forward your question to sir so that he can answer your question. Coming to your material and software details, maybe we'll send you a mail, guys. Please give your feedback so that we can get back to you if you have any queries. Our details have been already posted in the chat box for the more details. You can also follow us on our Instagram and LinkedIn and YouTube page, which will help us to get back to you, and you will be updated from our recent things. And as we have already spoken about the next webinar on filtered design, maybe you can get our update from the Instagram and LinkedIn pages. You can also rewatch the complete session on YouTube. We have already shared our YouTube page. There's a question from Sairam. In this example, you have shown by using capacitors, your harmonics are increased, but how to minimize the harmonics for increasing power factor?
Yeah, means as of now, what I did is I just placed a capacitor, but actual capacitors will have a series reactors, which has to be fine-tuned with the system parameters in order to avoid any resonance. At the same time, we have to reduce the harmonic contents. That we can cover it in our next session. Like that will cover under the filter design part. Like at that time, I can show you a filter, how to design a filter, and after placing the filter, how it will reduce the harmonics.
There's a question from Venkata Nagesh. Sir, as an engineer, mostly where we are using this type of analysis, especially the harmonic?
So power system consultant, we need to see, like basically few of our clients come up with some queries saying that there is a damage in the plant or something like that. So that time we are doing a root cause analysis to find out the issue. We found most of the times it is because of the harmonic sources.
Okay, Sairam, we'll get back to you with the next session. Please follow us on the Instagram and LinkedIn. And there's a question from Vikram. Hi, sir. Where to place SVC and StatCom in system, and what is the cost?
Yeah. See, basically, as I told in my presentation, like at the PCC point, we need to limit the harmonics as specified in the IEEE 500 standard. Correct. So what I will do is always try to place a SVC or a StatCom which is very close to the source, where I would like to reduce the harmonics, basically on the medium voltages in the system.
Okay, there's a question from Maunika. So you're taking harmonic values in the PDF. Those values are taken at any particular instant or for a duration of time?
These are like guaranteed parameters. This will be like when you are running a converter, it will be a full like a continuous basis only. And it depends on like if you have a multiple converters or what we are doing in harmonics is the worst case simulation. Say suppose if you have a two converters with a slight different phase shift, they may get cancelled out each other. It will not be summation all the times. It means that whatever the converter they have specified, it is a guaranteed parameters the converter will inject into the system.
With respect to the type test or the routine test that they perform.
Exactly. This is what the parameters the vendor has provided, and it will be the guaranteed parameters in the system.
Okay. Yeah. There's a question from Joseph again. Sir, tell me the wireless high power transmission system. Joseph, we didn't get your question clearly. Could you please come up with a detailed explanation, like what exactly you're expecting from the question? Then we have a question from Sheikh Savali. From generating station to consumers, approximately how much loss of power take place in case of one substation? Okay.
Yeah. Is something statistics? I don't.
Yes, that depends upon the distance from the generating station to the first run substation. Again, like what is the type of the cable that you're using it, what exactly the loads that they're consuming, and there are many parameters that actually impact their tuple, right? I hope we answered your question. And there's a question from Maunika, sir. Due to voltage harmonics, current harmonics are produced, or vice versa? So, which are produced from what?
Basically, the loads will be of whatever the nonlinear loads, they will create the harmonic currents. This will cause a voltage harmonics in the source. When you are connecting, like you have two plants, plant 1 and plant 2. My plant 1 is something like a steel plant or something. It is creating so much harmonics, whereas the plant 2 will be a normal some small station trans or some station or something like that. It will, for that particular plant 2, it will have a voltage harmonics, because the voltage source harmonics are already got distorted because of the plant 1. Clear? Or? So basically, it's a to answer straightforward, like current harmonics will create the voltage harmonics. And because of the voltage harmonics in the system source, the other plants which are connected to that particular utility will have a distorted source voltage, which will create some harmonic currents.
Yes, I hope she got clarity on it. Right, any more questions, guys? Okay, great. Thank you so much, Santosh sir. I hope we are almost done with the session. Okay, we're getting questions. So how harmonics affect the transformers?
Yeah, as I shown you before, like if you are taking only the fundamental current, we are getting 156.3 amperes. Whereas if by adding the harmonic sources, harmonic current to the fundamental, there is a rise in the current, like from 156 to 160 amperes. We have seen by increasing the fifth harmonic current to 20%. Remember during the session. So that when we are doing any load calculations, or if you are sizing any transformer, we are not generally considering these harmonic currents in the design. So because of this, there is a overload on the transformer, and there is a heating efforts, and also there is a saturation efforts. There is a possibility of transformer going into the saturation during the full load condition. Because of this.
So yes. So there's a question from Venkat and Nagesh. Sir, these software will directly connect to our field network. Is it perfectly suitable? We can identify and overcome those harmonic problems. Yes, it's a real-time simulation software, so it will help you, right, sir? You can.
Yeah. Like actually, like based on my experience, like I worked on various industrial units, wherein I have collected the harmonic contents from the vendor, and I have done the studies with these kind of softwares. And in most of the cases, the results are almost matching with the site. There will be a slight differences because of the various factors, but most of the cases it will be higher. And also there is, like, we can also take, as a power system consultant, we need to consider some worst case conditions. We need to always go for the higher sides to get the more impact of harmonics on the system. So that will help us to analyze what is the exact harmonic contents in the system.
Right. Is solar plant on domestic houses inject harmonics in the system? Question from Vikram.
Solar. Okay. I think that has inbuilt filters, small filters provided by the solar manufacturer. Like the inverter itself will have a harmonic filter. Okay. It will get reduce the harmonics there itself.
Yes. Yeah. So thank you, guys. It was really a wonderful session with very quite interesting questions and good answers from Santosh sir. So please give your feedback, guys. you can contact us with giving your feedback. We will get back to you if you have any queries. Compared to the material and all those stuff, you will be receiving a mail tomorrow, guys. And if you haven't received your certificate, please wait for a week and then let us know. If you can reply on the mail, or you can contact us. I've given our details also. Please follow us for the latest updates regarding the webinars that we conduct. Any more questions, guys? Right. Thank you, sir. Thank you so much. Thank you, Santosh sir. It was nice time having you here.
Thank you.
Right. Hello, guys. Thank you.
Thank you.
Thank you. VHLW signing off. Thank you, sir.
Thank you. Thank you very much.